record. There we go. Cool. Okay, so welcome back. Another edition or another lab for the class. So just to clarify, last week we didn't have an R lab. Last week we went over the sample term test, and the lab session was basically devoted to filling out the solutions to said sample term test. And then those were posted online, and that was kind of that walkthrough is posted as lab number 4. So I called this lab 5 in the write-up. So there will be a gap, lab 3 to lab 5, on the course content page of the website. And again, that's just because of how the time was used last week. So we're going to return to a more traditional style of lab today. The focus of this lab, as described in the write-up that's given in the course content section. So again, I'm just going to kind of walk through the different aspects of that write-up and go over essentially what I'm doing in this lab is kind of explaining to you how I generated a lot of the results that were given in lecture set number 5. And then next week, we're going to look at lecture set number 6 and probably lecture set number 7 as well. So this lab is mainly an introduction to fitting GLMs in R. We're going to focus on binomial GLMs and in particular, the logistic regression model. Fitting these models is very straightforward. It's done through the GLM function, which I believe is in the base package. And for the most part, the output is pretty much exactly the same as the linear regression model. I'll talk about the different components of the output today. I'll highlight what we have discussed in lecture, so you understand where the parameter estimates are located, where the standard error is located. We'll talk about the associated test statistic and the p-value that's given with that test. And I will discuss the other output that we have worked with as well. And then I will also explain the 2 items that we haven't discussed in lecture formally, but we'll discuss tomorrow when we get to lecture set number 6. The other thing that I have in this lab is another formal process for fitting the IWLS, or another self-coded R function for fitting the binomial or the logistic regression model, in particular, the simple logistic regression model via the IWLS process. So again, this is code that is only going to work in the case that we're working with a simple logistic regression model. So that's a model with an intercept and 1 explanatory variable. But it's still, in my opinion, worth going through the coding of these types of functions just to give you exposure to the kind of higher level functionality of R. So with that being said, I'll start getting into the material. Okay, so this is our 5th lab. First part is the Beetle mortality data. So in lecture set number 5, we were working with the Beetle mortality data. Now, unfortunately, this data, as far as I know, is not available in R directly. So we can build a data frame ourselves. This is done in a pretty straightforward manner. So here I just have a vector Y, which is counting the number of deaths at each of the dosage levels. I have my vector N, which is counting the number of beetles that are exposed at each dosage level. And then I have the different dosages of carbon disulfide, and these are given on the log scale. So I can leave these as vectors if I want to, and I can still fit the GLM to these vectors directly. Or I can turn this into a data frame using the data frame function. Okay. Right, so if you do this, you can see that you end up with what looks like an R data set. So we have our 3 columns, N, Y, and X. It doesn't matter which order you put these in because you can pull the information out using the $ command. So you can see here I have Beetle's data N, Y, X as my 3 different options now. So I can easily extract columns from this data set simply using the $ notation, or I could even use things like matrix notation to pull out rows. So this would give me the first row, this would give me the 7th row, or I could isolate individual observations. So row 7, column 3, for example. The nice thing about putting it into a data frame is simply that when we are building the GLM, we can use data equals and specify Beetles.data so that R knows where the variables are coming from. Again, you can do this without specifying the data set as well. So you can directly just plug the vectors into the GLM function and not give the data set, as long as Y, N, and dose are saved into the working space. R will know what those vectors are, so it can pull that information directly. All right, we can also visualize this data like we did in the lecture set. So what I'm going to do here is create a scatter plot that plots the dosage level on the x-axis and the proportion of deaths on the y-axis. So I'm going to use the data frame commands just to show how that would work. And now I'm just going to label the plot. So I have dosage here. Proportion of dead beetles. My title. All right. And then here's my plot. And then I'm also just going to actually just add in a little customization here because I don't like the open circles. I'm going to close them. I prefer the closed dots. Okay, so this is the same image that was generated and utilized in the lecture set. You can see here, as we discussed in lecture, this is very clearly like not really a linear relationship. We have a more of kind of an S kind of bowed out, I guess concave S type shape. And the proportion of dead beetles is obviously going to be constrained between 0 and 1 as per the definition of a proportion. So what we want to do is fit a model that will allow us to estimate these proportions directly. Okay, so we can do this using a binomial GLM, or in particular, a logistic regression model. Okay. All right, so in lab, we actually outline, or sorry, in lecture, we actually outline the process for fitting this model via the the iterative weighted least squares approach. So I've written up some code that will allow us to implement that approach. I'll go through that with you now. This code is available in the write-up, so I'll basically just use what I've already coded and kind of explain the steps to you since you have access to this. In that process, we can simplify the score functions and the information function in terms of the value pi hat, where pi hat is exp of beta 0 plus beta 1x divided by 1 plus exp of beta 0 plus beta 1x. So what I've done is, rather than having to continually code this expression here within my IWLS procedure, I've built a separate function that will directly compute pi, such that I can just reference this function and then call that within my IWLS procedure. So this first approach here is simply a function that's going to allow me to compute the value, which I called pi est, based off of this expression here, which is given in the log likelihood function and the score functions for beta 0 and beta 1. So this computes pi hat given B0 and B1. All right. Now, I've also coded up the likelihood function for this particular problem. And in this case, you don't actually need the log likelihood function to run the algorithm, but I wanted to include it because I want to talk about a discrepancy between what was reported in lecture and what the log likelihood function actually computes, which is also a discrepancy between what R is going to output and what the textbook references that or the textbook chapter references that I gave at the end of the lecture set. So this is sort of just a little interesting aside. It's also important to see how the log likelihood is improving after each iteration, because again, what we're doing here is maximizing the log likelihood. And when we talk about penalizations of the log likelihood via AIC and BIC, which is something we'll discuss tomorrow, it's very important that you understand that when we're penalizing, we are reducing because we are finding the maximum value of the log likelihood. And this helps us to understand what value we should be looking for when we are comparing the different values across different models. Okay, so this here is going to compute the log likelihood given B0 and B1. You'll see also that this includes Y, X, and little n, which are constants from the data set. So not values that are going to change, but still required to get the computation. Okay, so I will now share with you the code I wrote to implement the algorithm. Again, we've seen an example of this already, and the procedure is identical to what we saw before. So I'll just walk through the code with you. You have access to this via the written notes, and I will post the code after class as well. But most of this is identical to what we coded when we discussed the Poisson model and the IWLS procedure for the Poisson model. The only difference is the updates that are given within the for loop. Okay, so I've called this IWLS.log, so IWLS for a logistic model. My inputs are the data, B0, B1, and the number of iterations that I would like to consider. All right, once I've imported the data, which in this situation is going to be the data frame that I created at the start of the lab, I'm going to extract the 3 different components because of how I structured the log likelihood function and because of the form of the updates for the score functions and the information function. So with that being said, you might prefer to just input Y, X, and N directly rather than input it as a data frame and extract it. It's sort of a roundabout way or kind of an extra step that isn't really needed because we coded the values because we had to implement the values directly as vectors. But if we were running this on a data frame, we would have to have this kind of extraction line. So I think it's good to see both, to see it through this lens, because typically we're going to have to extract values from data frames anyways. All right. The next thing I did was opened a null vector to store my log likelihood values. Then I created a matrix to store my coefficients for B0 and B1. Okay, so this is similar to what we saw before. So this is a 2 by number of iterations matrix. So I'm going to put B0 estimates in the first row, B1 estimates in the second row. I labeled the columns, so I have the iteration number on the column, and I labeled the rows so I know which parameter I'm estimating. And then after I created my matrix, I computed the log likelihood given my initial value for B0 and B1. So this is just so I have a reference to know where the algorithm is starting, and then I'll let the algorithm progress to, from the starting values to the converged values. And I can track the likelihood in this way. So this is my initial likelihood value given the initial B1 and B0. Okay. All right, and then I also stored my initial B0 and B1 values in the beta hat matrix, and they're going to get stored in iteration 0. All right, then I'm just opening a for loop. So the for loop is going to run from iteration 2 until the number of iterations that I specified. The first thing I'm going to do is compute that pi estimate value. So again, you'll recall that in the updates that are given in lecture set 5, so if you compare this to what we drove yesterday, you can see this pi value is again just this ratio here. So instead of having to type this ratio in each of the different spots that require pi, I'm just using a function to do it. I suppose I could also just do pi is equal to this ratio on the first line and then follow the same process. That would work as well. I just decided to build an extra function because I don't know, this is usually how I just like a lot of having different functions for whatever reason. Okay, so then after I get pi, I get my score estimate for beta 0, then I get my score estimate for beta 1. You can see that this is simply y minus n times pi. It's a very simple calculation. And then I'm going to create a matrix called SMAT, which is comprised of beta 0 and beta 1 evaluated at pi. The reason for this is because in the IWLS procedure, I have to do matrix multiplication. So I need the beta 0 estimates to be stored in the matrix so I can multiply them by the information matrix, or rather add them to the information matrix. And then I am going to compute the values of my information matrix, which is shown here. Okay, so in this case, I'm directly writing them into the matrix. All 4 of these components here, again, we drove in lecture yesterday. And then my estimate for beta hat on the iteration 2 is going to be the inverse of the information matrix multiplied by the information matrix times the beta values from the previous iteration plus the score matrix that I found using those same values. Okay, and again, this is just the general equation for the IWLS procedure, which is given in lecture set and we've seen before. Okay, so then beta on iteration I, the beta.mat column corresponding to this iteration is now going to give me the log likelihood value that I require. Or is going to give me the most recent parameter update. So I'm going to compute my log likelihood value, and then I'm going to run this again until convergence. All right. Okay, so that's pretty much all there is to it. So let's take a look at the output here. All right. Okay, so you can see that we ended up on iteration 5. We have beta 0 is negative 60.717. If you recall from lecture set number 5, this is the same beta 0 that we had at convergence yesterday. And beta 1 is 34.270. And here's the log likelihood value. Okay, so I talked about how there's a discrepancy between what is reported in R and what is reported in the lecture set. In the lecture set, our log likelihood value is something like negative 186.7-ish in this range. This discrepancy is due to the combination term that is given here. All right. So the idea, as far as I can tell, is this term is constant with respect to the model parameters. So when we write out the log likelihood function, if we write it up to a constant of proportionality, we can actually drop this term off and not include it in the calculation, because this term falls off when we compute beta 0 and beta 1 anyways. So whether or not we include this in the log likelihood function is, it doesn't make a difference in terms of finding the MLEs. So if we drop the value off, the log likelihood term is actually larger than what we observed in lecture set. But that doesn't matter because it's still being maximized at the same point. So this thing is just a constant that's basically scaling up and down the log likelihood function. So if you think about a parabola, when you add a constant to the parabola, you just shift it up and down the y-axis. It's the same thing with this log likelihood function. So this term here is this shifting the log likelihood function up and down. Right? Now, if we wanted to get the exact same value back, we can simply take the log likelihood values Okay, we can take the log likelihood values here and we can subtract off that constant. And if we do that, you can see then we end up with the value that was reported in lecture. So negative 186.2, sorry, I said 186.7. It should have said 0.2. All right, so the discrepancy here is due to the fact that the value that was reported in lecture and the value that was reported in the text chapter that I was working off of actually does not include that combination term. Now, this value here is computed using the full log likelihood expression as we drove it in class. And this is the same value that R utilizes when it computes its likelihood-based criteria. So with that point being made, it is fine to include all of the terms that are present in the log likelihood functions that we derive in lecture or for the models that we work with, because that is apparently how R does it anyways, which I'll show you why that's true momentarily. So this value here is not incorrect. And this value here is technically not incorrect either, because regardless of whether or not we include this term, you're still going to maximize at the same point. Okay. Any questions about that? All right. Okay, so keep in mind the values that we found at convergence of our IWLS procedure. What we'll now do is basically verify these values using the GLM function. So I'll call the output res1. So GLM is actually a very easy function to use. It's not really all that different from the LM function, outside of the fact that you need to specify the family you're interested in. You'll notice from the output here, the default family is the Gaussian model. So if we were to fit a Gaussian GLM and then use the LM function, that output should be the same in terms of the parameter estimates and the standard error. In our situation, we want to fit a binomial GLM. So when we're fitting a binomial GLM, we open up a cbind at the start and we type number of observed successes minus the number of observed failures. Okay, so when specifying a binomial model, this is the starting point. So you give successes and failures into the response variable slot. Then we say that this is a function of whatever explanatory variables we have. So here I have X, but it's easy enough to extend this to sort of like an MLR type situation just by adding in more explanatory variables to the framework. All right, then we specify the family. So that is binomial. Now, if we want to change the link function, we write link equals, and then we would type in the link that we wanted to work with. The default link function for the binomial is the logit. So if you do not put in anything here, it's automatically going to fit the logistic regression model. So that's the default binomial GLM. So whether or not we specify nothing or we write link equals logit, we're going to get the same output. So if we want to switch to a different model, all we have to do is change the link function here. And I'll show examples of that next week once we discuss those other models. All right. And then I just have to give the data frame. So the Beetle's data. So as I said, it's a pretty straightforward function to use. There's nothing too tricky about it. All right, so if we type this in, you can see here that we have our estimates, which match exactly what we gave above. Okay, and then you can see here we have the AIC. So the AIC is -2 times the log likelihood at convergence plus 2p. All right, so if we take 41.43 and we subtract 2 times the number of parameters, which is 2, and then we divide this expression by -2, you can see we end up with -18.715, which is the log likelihood that we get at convergence when we include the combinations term in the function. So again, by default, R is computing the log likelihood using the full expression that includes the combinations operator, whereas the reported value in the textbook I was working off of does not include this value. So the discrepancy is simply between this constant here. And again, the reason is, regardless of whether or not we include this constant in the calculation of the log likelihood, is somewhat irrelevant because it's going to drop off when we're finding the MLEs. So the function still gets maximized at the same point. It's just the value of that function is scaled based off of this constant. All right, so what we'll do now is talk about some of the output that's given in or from the GLM function. So the first thing is simply the formula that you used. Again, we didn't specify a link here, which means that it's a logistic regression model by default. The first column gives us the 5-number summary of what are called the deviance residuals. The deviance residuals are basically the terms for each observation that we add together to find the deviance. I'm going to define these formally in lecture set number 6, and I will also show you how we can compute these in R next week. But these deviance residuals, they can be used to check model assessment, because if we have enough observations at each, if the trial number little n is high enough for each observation, these should be approximately, well, the deviance residuals should be approximately chi-square distributed, but if we standardize them, they should be approximately normally distributed. So you can get some sense of how the model is fitting based off of these values, but most often we would simply refer to the residual deviance value, which is given here. And this residual deviance is the same thing as capital D that we were utilizing in the lecture. So you'll notice that we have 11.232 shown here. In lecture set number 5, our deviance was 11.23. So this is basically telling us the value of capital D and its associated degrees of freedom. And what we would do here is basically use this value to test if the full model is required. So this is the test statistic for the test. The fitted model is sufficient versus the alternative that the maximal model is required. And in this situation, as we can see, this value is almost twice the size of the degrees of freedom, which does imply that there's a bit of an issue with the fitted model. We'll talk more about that tomorrow as well. But it's also not significant at a 5% significance level, which suggests that the fitted model is sufficient compared to the maximal model. Right? Any questions on that? Okay. All right. These values here, I think, are fairly self-explanatory. This is our value for B0 at convergence. This is our value for B1. We talked about the interpretation of those values. Here are the associated standard errors. So these are found by taking the square root of the diagonal of the information matrix. We can use these values to construct a confidence interval. You'll notice that these are both normally distributed. So the confidence interval, as we showed in lecture, can be built using the standard normal distribution. We also have a test statistic based off of the estimate and the standard error. You'll notice that just like with regular R output, the test statistic is simply the estimate divided by the associated standard error, which is true in both cases. Right? So this value here is testing whether or not the coefficient is different from 0. Okay, so this is a standard two-sided test about B0, where let's say more generally, these are standard two-sided tests about beta j equal to 0 versus the alternative beta j different from 0. And in both cases, you can see that there's overwhelming evidence that these coefficients are different from 0. And in the case of the slope, this would suggest that there's a linear relationship between the dosage level and the logit of the probability of observing a death. So again, pretty much the exact same interpretation that we had in the case of the linear model. It's just that the response variable is the logit rather than just y directly, as it would be in the case of a normal linear model. All right. So we're going to talk about the AIC tomorrow, though I did do this transformation to highlight the log likelihood value at convergence. We'll give a strict definition of this in lecture, and we'll look at examples of how we can use this. Most often, it's just used in a model comparison style format. But again, I'll show you examples of that tomorrow. The other value in the output is the null deviance. So this value is the deviance measure for the logistic regression model with no explanatory value. So to explain what that means, we can actually fit this model using the GLM function. So we would have y n minus y given 1. Okay, so this is basically saying fit only an intercept term, right? So it's logit pi I equals beta 0. Okay, family equals binomial, Beetles dot data. Okay, so you can see here, there's that 284.2, which is the same value shown here. And basically what this is implying is that the null deviance, which is going to be reported for any GLM, is again a value that indicates is the model with no explanatory variable sufficient compared to the maximal model. And in this case, you can see it's overwhelmingly, or the evidence is overwhelming that the maximal model is a better fit, or there's overwhelming evidence that we would require the maximal model compared to the null model, as this particular test statistic is going to give a p-value on 7 degrees of freedom of basically 0, right? So I'll just, So we have H0, no, the null model is sufficient versus HA maximal model is required. Okay, so the test statistic is that 284.202. And then via R, we can show that the p-value for this test is this value here, right? And then if you wanted to, you could actually find the critical value as well. So the critical value is going to be the chi-square with 0.05 in the upper tail, 7 degrees of freedom, right? So you can see again, like based off either approach, if you take the critical value approach, that test statistic is buried in that tail. So that's well within the rejection region. And the p-value is effectively 0. So this gives evidence that the maximal model is required when alpha equals 0.05. Okay, so we have parameter estimates, standard errors, we have the Z scores for the test that the coefficient is different from 0. And this is a two-sided test using the standard normal distribution. And then we have the null and residual deviance. The null deviance is always the deviance score for the model with no explanatory values. The residual deviance is the deviance for the fitted model, and both tests compare to the maximal model. We also have the deviance residuals, which should be chi-square. I'll talk more about these tomorrow. And then we have the AIC, which is a likelihood-based criteria that we can use for model comparison. And I'll talk more about this tomorrow as well. This also gives the number of iterations to reach convergence. Notice here that this is saying it took 4 iterations to converge. We have 1, 2, 3, 4, 5 iterations based off our approach. So pretty close. All right. Okay, any questions? So the last thing I wanted to talk about is how we can utilize the model. So there are 2 functions that we can use to essentially get estimates of the response variable based off of the fitted model. They are the predict function and the fitted function. So I just want to talk a little bit about the difference between the 2. You can see that both are very easy to implement in R. So if we use predict, this is giving us the score of the logit of the probability of success for each of the different explanatory variables that are used in the model, right? So this is logit. Okay. And the fitted function gives us directly the probability of success. So in our case, this would be the probability of death at each dosage level, which is the probability of success for each explanatory value. Right. Now, so the fitted value is giving you pi hat directly, whereas the predict is giving you y as it would be y via the link function. So in our case, the logit of pi directly. So whenever we use predict, you are getting the raw value of the response with the link function attached to it. Whenever you use fitted, it's actually taking the fitted model and finding the underlying value for you. So in our case, or in any of the binomial cases, that would be the probability of success. So as I mentioned yesterday in lecture, this is one of the, one of the aspects of using R that is so, or any statistical software that's so helpful. Regardless of the link function we consider, in the case of the binomial models, we can easily extract the probabilities of success for those different values. Right? Now, from predict, we can also arrive at the fitted value. So to show you the relationship between the two, we know that predict is the logit value score. So if we take EXP of predict, this is going to give us the odds. And then if we take inverse logit of the predict, and the inverse logit function is available in Fairway. So if we go I logit predict res1, okay, so now if we compare these, oh, fair away, not farewell. I'm just gonna pop this part back up here. Okay. So now you can see here are the odds of death in this case. And if we compare the fitted value to the inverse logit of the predicted value, you can see we have the same numbers. So from predict, we can extract the inverse logit and the fitted value as well. There's one other thing I think, I'll see if I can figure it out fairly quickly here. I just thought of it. But there is a way we could define a value. I think you have to do it using a data frame. Okay, so I think we can do it like this. So if we go predict res1, and then we were to go new x equals, and then I think it has to be a data frame. Okay, got it. So suppose that we wanted to do some custom values. So maybe we wanted to try, for example, I don't know, let's try 1.77, I don't know, 1.75 and 1.8, try and keep it simple here. So we could do 1.75, 1.8, data.frame new underscore x. Oh. Oh, I see. There we go. So I don't even need this part. So if you wanted to do some custom predictions, you can do that as well. Yeah, thanks, man. Okay, so, and that's a helpful tool as well. I'm not sure, let's see if it works with fitted. No, it doesn't work with fitted. So then I guess you would have to, if you wanted to get the probabilities of success, you would have to just ILogit this thing, and that would give you the probabilities out. So pretty helpful tool to have, I would say. And then the last thing I wanted to talk about was just superimposition using the fitted values. So in lecture, I showed the fitted curve on top of the plot. And I made a little note. I don't know if you picked up on it, but I was like, it's a little bit chunky. So the way that the curve, if you look closely, you can tell the curve isn't smooth. It's kind of like they're just line segments between each of the points. So we can actually superimpose a nice fitted curve, and we can do that using the sequence command. So basically what we're going to do is build a nice smooth fit of our fitted model and then superimpose that on top. Okay, so what I suggest here is build a sequence from, you can pick your own starting values. I went from 1.6 to 1.9. I just kind of went outside the min and the max. I'm going to let the values differ by 0.01. Okay, so now what I'm going to do is I'm going to find the probabilities of success for the fitted model. And I'm going to do that at each of the different points here. So what I'm going to do, actually, I'm just going to try something really quick. I want to see if I can do it this way. Oh, nice. It's kind of cool. It's a nice little trick. So that's a different way from how I actually wrote it up in the lab, but it also illustrates how we can use the predict command. And then you'll notice I'm just sticking the ilog on the outside because I want those probabilities of success. And then for my scatter plot, I'm just going to add the fitted values that were given here. So I don't even need this part. Okay, and now we have a much nicer sort of smooth fit. And we can smooth this out even more just by further segmenting the points. Okay. And now you'll see when you look closely at this graph, unlike the one that I gave in lecture set, it's not just connected line segments between each of the points. This is actually a nice smooth fit showing the curve through this particular data set. All right. Any questions? Okay, I'm not seeing any. All right, so that's what I wanted to talk about today. So that's basically kind of an introduction to fitting GLMs in R. We're going to expand on these ideas next week. So I'm going to show you the other types of binomial GLMs. We're going to talk about model comparison. I'll show you how I kind of built the different, or I found the different model comparison criteria that I'm going to introduce to you tomorrow in lecture set 3. I tried to find a variety of them so we could really build a thorough comparison of the different models. That's going to be very important going forward, particularly on the project where you're going to want to compare models to one another, like for example, subsetted models to larger models, and that sort of idea. And then we'll also probably next week talk about fitting nominal logistic regression models in R as well. I think that's a topic we'll get to maybe tomorrow, most likely on Tuesday. And I'll introduce in lecture kind of the theory, and we'll go through some examples of interpretation, and then I'll show you how to fit those as well. All right, so I will wrap it up here for today. And then of course, I'll hang around until the end of the section, which is about an hour from now. We have assignment 2 due on Friday. So if you have any questions about that, I'm happy to take them. Or if you have any questions about any of the stuff we discussed today or any of the material we've been talking about, happy to take those questions as well. Otherwise, if you're going to take off, I'll see you tomorrow. And thanks for attending.